Let me continue with this discussion of hypothesis testing. Last time I went over the sort of framework, the process of hypothesis testing, and I indicated that this week I would go across some examples, go through some specific examples, and I will do that. I'd like to go through 3 examples today and then post some example problems on WebCT. Let's start with problem 3 on page 182. Problem 3 on page 182 says, a sociologist has been hired to assess the effectiveness of a rehabilitation program for alcoholics in her city. The program serves a large area and she does not have the resources to test every single client. Instead, she draws a random sample of 127 people from the list of all clients and questions them on a variety of issues. She notices that on the average, and I will reword this, a sample appears to miss fewer days of work each year than the city as a whole. Are alcoholics treated by the program more reliable workers? The first thing that one might notice is that the size of the sample. 127 people in the sample. Would you agree then that sample size is large?
Yes.
If sample size is large, you conduct a z-test. Only if sample size is small do you conduct a t-test. So in this instance, we're going to conduct a z-test. And the process, as I said last time, is a 3-step process. First of all, to define the critical value of z. Second, to compute an observed or obtained value of z. And finally, to compare those 2 scores in order to evaluate the null hypothesis. Let's take a look first at the critical value of z. In order to determine the critical value of z, we said that we needed 2 pieces of information. First of all, the level of alpha. And let us assume that alpha is 0.05. We set alpha equal to 0.05. The second piece of information we needed was the number of tails in the test. And this hinged upon the research hypothesis. The research hypothesis specifies some relationship between x bar and mu. What is the research hypothesis here? Is it x bar will be different from mu, x bar will be less than mu, or x bar will be greater than mu?
It will be greater than mu.
One person says that the research hypothesis is that x bar is greater than mu. Do we all agree on that? Yeah? Then we're all wrong. You determined this you're very surprised, aren't you? Because when you look at this last sentence in the problem, it says, are alcoholics treated by the program more reliable workers? And you looked at the notion of more and said greater than, yeah? In this specific case, what does more reliable mean? Just, what does more reliable mean? You can either read the problem as a whole, or at least the sentence before the last one.
Okay. Because the first one indicates that her sample misses fewer days, therefore they would be more reliable. So it would then be less.
I would agree with that. so would everybody else. They followed you off the cliff before, so I don't understand they wouldn't follow you off the cliff this time. The logic is this, as to why its x bar is less than mu. The last sentence says, are alcoholics treated by the program more reliable workers, which would imply a research hypothesis, x bar is greater than mu. This group the sample will be more reliable than the population. But the notion of reliability is measured in days absent from work. So that the more reliable you are, the fewer days you are absent from work. So we could, the second last sentence says, she, the researcher, notices that on average her sample, and I'm rewording here, appears to miss fewer days of work each year than the city as a whole. We could then rewrite the last sentence. Do alcoholics treated by the program miss fewer days of work than the city as a whole? Which I think will make it clearer that then the research hypothesis is that x bar will be less than mu. Before we go to the number of tails, this means that the null hypothesis is that x bar will be greater than or equal to mu. The null hypothesis is simply all the possibilities not included in the research hypothesis. Let me ask, however, let's go back to the research hypothesis. If the research hypothesis is that x bar will be less than mu, is this test going to be one or two-tailed? Would you agree, those of you who didn't answer, that this test is going to be one-tailed because you have to test only for negative difference and not for both negative and positive difference? If the prediction is that x bar will be significantly less than mu, why test for the possibility that x bar will be significantly greater than mu? What you're doing is you're testing for negative difference and establishing some region at the negative tail of the distribution that contains, since alpha is 0.05, 5% of all of the scores in the distribution. 95% of all of the scores will be in here. And the logic, if you recall, is that you will reject the null hypothesis only if this single sample mean, when standardized, is in this critical region, that it's an unusual or rare event. But we will go over that more fully when we arrive there. As Bob Dylan said, we'll cross that bridge after it's gone, after we're way past it. I love that. So if alpha is 0.05 and it's a one-tailed test and we're testing for negative difference, what is the critical value of Z?
Negative 1.96. Plus or minus?
A first answer of minus 1.96 and a second answer of plus and minus 1.96. We can deal with the second one very easily. It's certainly not plus and minus 1.96 because that would suggest that we were conducting a two-tailed test. So I'll give you all y'all. I'll give y'all another try. What is the critical value of Z? I'm sure this is in your notes, and I'm sure it's on page 193 of the text. But absent that, those two sources, I don't know where on earth you'd come up with the answer to this question.
1.65.
Would you like to refine your answer?
Negative 1.65.
Would anybody else agree with minus 1.65? For the lemmings in the crowd, I don't have to take the exam. And in the exam, I don't think anybody's going to stand up and volunteer that the critical Z value in question 1 is minus 1.65. So you might want to learn how to work your way through this. We have now a critical value of 1.65. That is, if you go 1.65 standard deviations below the mean, you isolate 95% of the scores in the way that we've discussed, leaving 5% of the scores at the negative end of the distribution. What is more, since we've measured this distance in standard deviations, that is, we know that this point is 1.65 standard deviations below the mean, we have to, as a second step, compute Z obtained. That is, we have to convert the sample mean into a Z-score. We have to standardize it. You're given the information for the problem on page 183. You're told that mu is 7.2 days. You're told that x bar is 6.8 days. You're told that sigma, the population standard deviation, is 1.43. And you're told that n is 127. Does any brave soul care to tell me what the formula for the computation of Z is in this situation? This is a situation in which you're comparing x bar with mu, n is large, and sigma is known.
It's situation 1,
Yes.
x bar minus mu over sigma divided by square root of n.
It's situation 1, as we labeled them, so that the formula for Z obtained is the sample mean minus the population mean divided by the standard deviation of the sampling distribution of sample means, which is sigma over the square root of n. And if you simply plug in the numbers now, x bar is 6.8 minus mu, which is 7.2, divided by sigma, which is 1.43, divided by the square root of n, which is the square root of 127. And if you perform that computation, at least according to Healy, the answer is minus 3.15. That is, Z obtained equals minus 3.15 standard deviations. Are there any questions on the computation of Z obtained? Let's go back then to the diagram here. We can now place the single sample mean of 6.8 into this standardized normal distribution. It lies 3.15 standard deviations below the mean. At the center here, would you agree, is 0 standard deviations. So we travel out past 1.65 down to minus 3.15 standard deviations. Do you reject the null hypothesis, or do you fail to reject the null hypothesis? there are 2 or 3 people nodding their heads like, yeah, I'm sure of that too. You reject the null hypothesis. This is a rare event. The height of this curve measures the frequency with which these various scores appear. That is, 0 standard deviations, in this case mu equals 7.2, occurs most often. Minus 1.65 standard deviations occurs less often. And minus 3.15 standard deviations occurs less often still. This is a rare event. It is distantly removed from the average, from the mean. And you would therefore conclude that it is significantly different from the mean. In fact, you would support the research hypothesis, which says not simply that it is different, but that it is significantly less than. You would therefore reject the null hypothesis and conclude that indeed alcoholics being treated in this program miss significantly fewer days of work per year than the city as a whole. Are there any questions? No questions? Well, I'm having so much fun. You have a question. I'm not interested in your question. I was having so much fun, I was going to do another. But I'll answer your question first.
This may seem a stupid question.
Don't worry about it.
Based on the numbers that we got on the second step, I know where we got the 127 for n, but the other numbers based on the problem in the book, did we derive that from that or just on the next page?
They're given to you on the next page.
So we don't have to worry about
you're
figuring
given
them
the
out.
problem on page 182, and the only data, as it were, that you're given there is there are 127 people in the sample. What you give on at the top of page 183 is the rest of the relevant data.
So we don't have to worry about figuring that stuff out. It'll probably be
Oh
in the
no,
problem.
you have to be given all of that information. Let's then do another question.
Yeah. Can we do one where
No, can you press and hold?
Can we do one where n is small? Cause we're
Oh, you want me to do requests now?
Please?
This is like, what is it? KLOL at lunchtime. You just phone in and take control of the air. If I was headed, actually, to where was I headed? I'm just simply thrown right off now. I'm simply thrown off. I was headed to page 199. I was headed to the problem that starts about a third of the way down page 199 that says, a researcher wonders if commuter students are different from the general student body in terms of academic achievement. Let's not go any further. Well, yeah, let's go further. What I was going to do was define the research hypothesis right there. But let's go further. She has gathered a random sample of 30 commuter students and has learned from the registrar that the mean grade point average for all students is 2.50. But the standard deviation of the population has never been computed. Sample data are reported below. Is the sample from a population that has a mean of 2.5? Forget the last sentence, because it is simply framing in yet another way an issue that we have dealt with repeatedly. And it's the nature of the research hypothesis. And you're then told that mu is 2.5, x bar is 2.78, s is 1.23, and n is 30. Would you agree that n is small? Yes. So that you can, n is below 100, n is 30 here. So that we're going to conduct a t-test and not a z-test. The first step then is to define the critical value of t. And in order to do that, you need to know three things. You need to know the level of alpha, you need to know the number of tails in the test, and you need to know the degrees of freedom. Degrees of freedom. We'll work our way down here and come to grips with this. And this is the only difference between a t-test and a z-test. It's not in the computation of t, of the observed value of t. The difference is in how you define the critical value of t. You need an additional piece of information. You need to know the degrees of freedom, number of degrees of freedom in the study. Let's set alpha equal to 0.05. Is this a one or two-tailed test? We have somebody saying quite confidently this time, even smugly two-tailed. There's somebody else saying two-tailed. We have somebody at the front taking the opposite tack that it's one-tailed. What is the research hypothesis here? What is the proposed relationship between x bar and mu?
That X bar is not equal.
It's all right. Would you rather talk about Manchester United's game this afternoon with Real Madrid?
Yes.
In the Bernabeu? What sort of formation Alex Ferguson will put out there, whether it'll have Van Nistelrooy leading the attack alone, put Keane back in defence out of midfield and play five at the back? Yeah? Would you like to speculate on how that will influence Zinedine Zidane in the Real Madrid midfield? Would you like to talk about the long-term causes of World War I, economic upheaval in Europe, the rise of Prussia, Germany, the system of alliances that was created? None of that's going to be on the third exam. Let me ask you, what is the research hypothesis here? What do you want me to put between x bar and mu? That they are not equal, that they, and why do you want me to do that? Press and hold. Press and hold.
Because in the problem it says if commuter students are different from the general student body.
Absolutely. In the problem it says a researcher wonders if commuter students are different from the general student body in terms of academic achievement. It doesn't say whether they outperform the student body, and it doesn't say wonders whether they're outperformed by the student body. It's simply a proposition of difference. If it's a proposition of difference, how many tails are to be tested? Some of you are saying two, and others look like they're calling for a curveball somewhere on the outside. Two? I'd agree with two. Because you have to test for both positive and negative difference. You have to test for the possibility that x bar will be greater than mu, that is positive difference, and the possibility that x bar will be less than mu, that is negative difference. So the test is to be two-tailed. Let me say something about degrees of freedom. And this is an aside, but I feel obligated, won't be on the exam, I feel obligated to say something about degrees of freedom and not simply tell you how to calculate them. Degrees of freedom are the number of scores free to vary if you know the mean. Let's assume we have three scores, x1, x2, and x3. And suppose I tell you that the mean of those three scores is 4. Can you tell me what the three scores are? The correct answer here is no. So at least one score is free to vary. If I tell you that the first score is 6, can you tell me what the value of x2 and x3? No. So at least the second score is free to vary. If I tell you that x2 is 4, can you tell me the value of x3? I would agree, yeah, you can. You can tell me, and more specifically, you can tell me that it's 2. That is, in a group of 3 scores, if you know the mean, only 2 are free to vary. More generally, in a group of n scores, n minus 1 are free to vary, so that degrees of freedom are given by n minus 1. Which, would you agree, in this case is 29, 30 minus 1. Yes? Are there any questions about establishing any of these pieces of information? Alpha, the researcher establishes for herself or himself. On an exam, you will be given the value of alpha. The number of tails in the test depends on the research hypothesis. If it is simply an hypothesis of difference, then the test is to be two-tailed. And the degrees of freedom are given by n, the number of people in the sample, minus 1, which in this instance is 30 minus 1, which is 29. How does all of this help you to define the critical value of t? Well, I bet you it has something to do with the text. I bet this little rascal Healy, swine that he is, has an appendix at the back of this text that has to do with t-scores. And sure enough, on page 465, you see Appendix B entitled Distribution of T. You see arrayed across, it says level of significance for a one-tailed test. Yes? Yes? And then you have values that range from 0.10 to 0.0005. Those are alpha values. You then have level of significance for a two-tailed test, and again you have a selection of alpha values. We're conducting a two-tailed test with alpha equal to 0.05. Would you agree that we're interested in the column of scores headed 12.706? In order then to determine the critical value of t, you simply have to go down the degrees of freedom column on the extreme left to 29 and go across the row until it meets the column of scores headed 12.706. And if you do that, would you agree that you find the score 2.045? So that the critical t value here would you agree, is plus and minus 2.045? Are there any questions regarding how to establish the critical value of t? Let's then compute the obtained or observed value of t, which is the second step. And to do that, you rely upon the formula for z, and that is x bar minus mu divided by s over the square root of n minus 1. And given the data here, that translates to x bar is 2.78 minus mu, which is 2.50, divided by s, which is 1.23, over the square root of n minus 1. N is 30, so the square root of 29. Are there any questions, first of all, on why we invoke this particular formula, or second, on how we move to this specific formula? According to Healy, if you perform this computation, it equals plus 1.22. That is, the obtained value of t is plus 1.22. The critical value, if you recall, was plus and minus 2.045. We're in this situation. We have the standard normal curve. We have boundary markers at plus and minus 2.045 standard deviations above and below the mean. We're isolating 95% of all of the scores. 2.5% are at the negative end of the distribution, and 2.5% at the positive end of the distribution. We have a z-score of plus 1.22. That is somewhere in here. Yes? Do you reject or fail to reject the null hypothesis? This should be the... Is this score critically... First of all, is it a rare event? Does it occur with great frequency? Is this score distantly removed from mu at the center of the distribution? It is not a rare event. It is not in one of these shaded regions. It is a fairly common event. It occurs with some fairly high frequency, and it is fairly close to mu, close to and therefore similar to the center of the distribution mu. You therefore fail to reject the null hypothesis. And you conclude, in fact, that there is no significant difference in the academic performance of commuter students and students as a whole.
Last time we had a number to compare it to, like to put it in, and there's no number.
There is. I just didn't put it in. This is minus 2.045, and this is plus 2.045. That's when we used Appendix B, you recall, to compute, to define the critical value of t.
Yeah, it just makes it easier to see where the other number goes.
Yeah. I'll be sure to tell them to deduct $50 from my pay. Okay, add $50. Are there any questions about this problem? Let me do one more problem, and then I will feel confident that you can effectively work your way through assignment 6. Let's look on page 202 at application 8.2. In a random sample drawn from the most affluent neighborhood in a community, 76% of the respondents reported that they had voted Republican in the most recent presidential election. For the community as a whole, 66% of the electorate voted Republican. Was the affluent neighborhood significantly more likely to have voted Republican? And then you're given the information, but you've already been given much of the information. The only thing you need is sample size. Would you agree that we're dealing here with proportional data? We're in what we labeled, identified as situation 4. Yes? We therefore are back to conducting a z-test. And the first step is to define the critical value of z. Let's say alpha equals 0.01. The number of tiles is equal to what? Okay. A fairly confident cry for 1.
Because it says, was the affluent neighborhood significantly more likely to have voted?
Not only a confident shout for 1, but an explanation. And the explanation is that in the problem, in the scenario, there is a line, a sentence that reads, was the affluent neighborhood significantly more likely to have voted Republican? It seems to me that that implies a research hypothesis that says P subscript S, the sample drawn from the affluent neighborhood, would be significantly more likely to have voted Republican than the community as a whole. That is, the research hypothesis is not simply one of difference, but difference in a particular direction, so that the required test is one-tiled. If alpha is 0.01 and you're testing for positive difference, and it's a one-tiled test, what is the critical value of z?
Plus 2.33.
I would say that it's plus 2.33. You're testing for positive difference, so the critical value of z is positive. And yes.
Where did that number come from? 2.33.
It can come from 2 or 3 places. It could come from the z table, if you were to go back and use it, but in the most efficient way, it comes from page 193 in the text. Or it could come from your notes. Yeah, we talked about there being 4 values now. In the context of interval estimation, we talked about 2 values. One associated with 95% confidence levels, one with 99% confidence levels. That is alpha equal to 0.05 and 0.01 respectively. We're still in that situation. And this person is still tapping his hammer. I think he got lost, got separated from the rest of the group. We're now, however, in a situation where we have not simply alpha to be concerned with, but the number of tiles, 1 and 2. And I think that that's then presented to you in table 8.1 on page 193, and I dealt with it, I know, last time. But and those scores all derive from Appendix A. Yeah? Forgetting is fine. It's all right. So, are there any other questions? Then we need to compute the obtained value of Z. I feel like one of those military analysts, sitting up here. I could be drawing sweeping arrows and, or just reading the news. In reading, I need a female partner, of course, because it has to be 3 words, 3 words, 3 words. Unless you're Peter Jackson, I guess. Is it Peter Jackson? Peter Jennings, not Peter Jackson. Peter Jennings, ABC. I know where he is. A young Canadian guy. Well, middle-aged Canadian guy. Older middle-aged Canadian guy. Yeah. I could be talking about Baghdad, Afghanistan. I know how to pronounce these words. I even know how to pronounce Caribbean, which is not Caribbean. And garage. Okay, Z obtained. The Z score is given by the formula P subscript S rather. Well, let's get rid of that. P subscript S, the sample score, minus P subscript U, the population score. This is analogous to X bar minus mu. Divided by the square root of P subscript U multiplied by 1 minus P subscript U over N. Let me ask you, what is the value of P subscript S in the current problem? .76, and P subscript U, would you agree, is 0.66. I make a point of this because in the scenario itself, you're not given those data as proportions. You're given them as percentages. 76% and 66%. You have to convert those percentages to proportions. That is, you can't put in 76 minus 66. You have to, just as in the context of interval estimation, you have to convert those scores to proportional scores. Divided by the square root of P subscript U, which is 0.66, multiplied by 1 minus P subscript U, that is 1 minus 0.66, which is 0.34, divided by N, which in this case is 103. Are there any questions about the general formula or translating that into the specific example? Yes.
How did you get the 0.34? I mean, I know it's 1 minus 0.66. But
well, if you know that it's 1 minus 0.66, what is 1 minus 0.66? It's 0.34. Kemosabi. Are there any other questions? If you perform this computation, Healy says that the answer is plus 2.13. Let's go back here. We have our sampling distribution now of sample proportions. P subscript U at the center. Our critical value is plus 2.33. That is 99% of all of the scores are in this region and 1% in this region. We now have an obtained z-score of plus 2.13, which is somewhere in here. Do you reject or do you fail to reject the null hypothesis?
Fail to reject.
If anybody, is there any ambiguity, uncertainty in anybody's mind about whether you reject or fail to reject the null hypothesis? You fail to reject the null hypothesis. This event is not a rare event. It occurs with some substantial frequency. It is not sufficiently removed from the mean, the center of the distribution, to conclude that it differs from that score. You therefore fail to reject the null hypothesis and conclude that the affluent neighborhood was no more likely to vote Republican than the community as a whole. Enough said. We've now looked at an example of situation 1, which can be used as well essentially as an example of situation 2, the only difference being that in 1 you know the sigma and in 2 you do not. We've looked at situation 3, a situation in which n is small, so that the test is a t-test and not a z-test. And we've looked at an example of situation 4 where you're dealing with proportional data. I will post assignment 6, which will be test problems that will look very much like the problems that you will see on the exam, except in this regard. You, on WebCT, you will be given a scenario, and then underneath that scenario you will be asked, A, what is the critical score, B, what is the observed score, and C, do you reject or fail to reject the null hypothesis. On the exam, those will be 3 separate questions. The first question will be, what is the critical value? The second question, what is the observed value? And the third question, do you A, reject the null hypothesis, B, fail to reject the null hypothesis, and so on. That is, each of these problems will be worth 3 points. 1 point for the critical value, 1 for the obtained value, and then 1 for evaluating the null hypothesis. But you're asked to do that in assignment 6, although it doesn't look precisely as it will look on the exam. Are there any questions? We will meet again on Thursday when, all things being grand and a miracle occurs in Spain, Manchester United will have beaten Real Madrid.